Lately, a specific rumor has taken hold across engineering teams. Retrieval augmented generation is dead. The assumption is that expanding context windows and autonomous tool calling agents have rendered external retrieval pipelines completely obsolete. Test that assumption against a real enterprise environment, and the cracks appear immediately. A user asks an internal AI assistant a specific question about a cancellation. The system retrieves the document, processes the text, and confidently issues a guaranteed refund, complete with a fabricated citation to an internal policy that actually expired 3 years ago. The concept of fetching external data didn't fail in that scenario. What failed was the specific implementation known as naive vector search. The standard baseline, often called chunk and stuff RAG, involves splitting text into random sizes, throwing those chunks into a vector database, pulling the top 5 results, and pasting them into a prompt. That architecture was designed as a beginner demonstration. It was never built to serve as a resilient production environment. RAG functions as a multi-stage system design pattern that requires rigorous engineering, testing, and continuous feedback loops. As long as artificial intelligence models require access to fresh, domain-specific, and permission data, a robust retrieval system is strictly mandatory. You cannot solve an authorization or data freshness problem by simply making the model larger. Deploying reliable enterprise AI requires abandoning naive data guessing in favor of deterministic retrieval control. In this 6-node linear flowchart, you start with raw documents and move through the pipeline to the language model. The core vulnerability sits in the retrieval logic, assuming semantic similarity equals factual relevance. We break this pipeline at its very first point of failure. Zooming in on the ingestion phase, we find arbitrary text chunking. Imagine your documentation contains this specific business rule. Because naive chunking relies on hard character limits, it routinely slices right through conditional logic, physically separating the strict requirement for finance approval from the main refund policy. When the user asks if they can get a refund, the retriever only pulls the primary clause. The language model receives that isolated text and cheerfully hallucinates a guaranteed approval, completely blind to the missing finance condition. Good chunking preserves structural meaning. It respects document headings, complex tables, and logical dependencies, rather than treating intricate business rules as random strings of characters. If the structural integrity of your data is destroyed at ingestion, no foundation model downstream can salvage the factual truth. In this 3-dimensional vector space, nodes are mapped by semantic proximity. The top K constraint blindly grabs the 5 most mathematically similar chunks to the query point, regardless of their actual utility. This creates our second failure mode. The highest scoring semantic match is frequently wrong. These nodes share identical keywords, but mathematically close facts are often practically useless. The precise, accurate answer actually sits further down the ranked list. It shared fewer overlapping words, so the algorithm pushed it away. Vector databases are highly optimized for broad recall, pulling in a wide net of potential matches. But a production application requires sharp precision. To bridge that gap, you introduce a reranker module. This acts as a rigorous secondary filter. It evaluates broad candidates strictly against the specific utility of the user's actual question. Without a re-ranking layer, the retrieval system is guaranteed to deliver what is plausible rather than what is correct.
In enterprise deployments, plausible answers break user trust permanently. These failures start before the database is ever queried. Real users do not ask clean, perfectly formatted keyword questions. They ask messy, highly contextual questions. Take a simple user query. Can I cancel after renewal? To answer correctly, the system must pull out the specific intent regarding policy, map the time constraint, and identify the billing source. Embedding that raw sentence directly into a vector database without parsing those variables guarantees an unfocused, irrelevant retrieval. A production architecture requires a query understanding layer at the very beginning. This gateway rewrites the query, classifies intent, and extracts metadata filters before the search begins. From there, the system needs hybrid retrieval. Pure vector search notoriously fails to recognize exact identifiers, like specific invoice numbers, version codes, or precise legal phrasing. To solve this, you combine the semantic connections of dense vector search, the exact term matching of sparse keyword search, and strict metadata boundaries. Relying on a single embedding search to solve every edge case is an architectural dead end. Production retrieval orchestrates multiple signals simultaneously. This brings us to the primary counterargument against RAG. Foundation models now possess massive context windows, capable of processing millions of tokens. If a model can theoretically read an entire company's documentation library in a single pass, why engineer a retrieval pipeline at all? The operational reality of massive context dumps tells a different story. Shoving hundreds of thousands of pages into every prompt creates extreme spikes in compute cost and unacceptable processing latency. This illustrates attention dilution. The model retains information at the edges, but loses critical facts buried in massive data blocks. Furthermore, dumping raw context introduces a security flaw, violating the principle of least privilege. In modern architectures, retrieval acts as a precise control mechanism for relevance, latency, and data access. Long context models do not kill retrieval. They simply shift where the retrieval boundary sits to guarantee cost efficiency and security. Returning to our evolving pipeline, we reached a critical phase where data is finally handed off to the language model. In naive prompting, pasting a random pile of retrieved chunks forces the model to expend compute power guessing the relationships between disparate facts. To prevent this, you insert a context assembly module. It explicitly maps retrieved text to timestamps, exceptions, and named sources before generation. Then, it passes through grounding verification. The verifier proves the model's claim is directly supported by retrieved evidence. Tracking all of this requires absolute observability. If you do not log the exact re-rank scores, the initial query intents, and the specific trace pathways, debugging a bad answer is completely impossible. This leads to the ultimate standard that separates serious engineering from industry hype: evaluation sets. This evaluation table shows the metrics a real team tracks. It maps expected document sources against actual retrieval performance, checks the grounding limits, and registers strict pass or fail states across hundreds of edge cases. Operating a generative system without evals and detailed tracing means you are managing a black box based on intuition, not an engineered application. We arrive at the final misconception: the idea that autonomous agents are a direct replacement for retrieval systems. The two approaches serve distinct functions. RAG provides necessary external knowledge, while agents utilize tools to execute actions based on that knowledge. Agents actually amplify the need for rigorous retrieval. A support agent must successfully pull the correct business rules and user history before it can safely alter an account. The stakes elevate significantly. If a standard chatbot retrieves the wrong context, it delivers a wrong answer. If an autonomous agent retrieves the wrong context, it takes a wrong, potentially destructive action. This brings our fully realized production architecture into view. It is an orchestration of query intent, hybrid routing, re-ranking, structured assembly, verification, and an unbreakable evaluation loop. The basic, naive retrieval pipeline is dead, but architecting deterministic, verifiable data pipelines remains the absolute bedrock of all trustworthy AI systems.